Hello everyone. So my name is Martin Lacroix, and I'm here today to present a collaborative work that is done at the University of Liège about the application of the particle finite element method and the finite element method in multiphysics simulation. And by multiphysics here, I will mainly focus on fluid structure interaction, but I will also show other kind of physics that can be simulated with this method. The presentation is subdivided in two parts, with the first part being about, well, the methodology. So I will explain here a bit what is the main idea of the particle finite element method that I will call PFEM for the rest of the presentation. Some explanation about the free structure coupling and how all of this is implemented in a code. And the second part is more about the test case. So I will show here what can be simulated with some video and colors. So the PFEM is very similar to the classical FEM in the sense that we will build a mesh and we'll solve the equation of, in that case, the fluid on this mesh. We are working within a Lagrangian framework, meaning that the mesh will deform with the movement of the fluid, and the nodes will follow this movement too. Meaning that if we use a classical finite element method, at some point, due to very large deformation of the fluid domain, especially if we have free surfaces, we may obtain very, very distorted elements, and the solution will no longer be correct. So you can see here some kind of block of fluid that will flow due to gravity, and well, at some point, the mesh will be no longer valid. And the main difference that we introduce here with the particle finite element method is that at some point, for instance, here in the second step, we will repair the mesh or create a new mesh with better elements so that the element will keep a correct shape during the whole simulation. And so how are we doing this? Is that when needed, we'll simply destroy the mesh and keep only the particles. So this is an example of a solution that has been obtained, for instance, at the previous time step, or simply an initial condition. We will apply what we call the Delaunay triangulation that will simply connect all the nodes in order to build a mesh. In 3D, this is exactly the same idea, but we call this a tetrahedralization, as we will link the nodes by tetrahedrons. And then we need some post-processing. And one of the most important post-processing criterion is called the alpha shape criterion that will remove elements based on their circle radius, meaning that the elements that are simply too large or too distorted compared to some characteristic element will be removed. And well, you can see in that example that we remove the nodes connecting the two parts of this, I may call this a fluid, but this is simply an example. But this post-processing criterion, so the alpha shape alone, is generally not enough to obtain a good mesh. We may also want to add or remove nodes depending of the location. For example, if two nodes are very close from each other, you can see here on this example that this will obviously create an element that is quite small, so we may want to remove one of the two nodes to create elements that are more or less uniform in terms of size. We may also want to add elements, to add nodes within elements that become a bit too large in order to prevent hole from being created in the fluid. And another very important post-processing criterion is what we call the point in polytope for polygon in 2D or polyhedron in 2D algorithm that will detect whether or not a node or an element is inside some closed surface, and this closed surface can represent, for instance, a solid that lies within the fluid, where you obviously do not want any fluid or node or element to be created in this solid, so we may remove it using this algorithm. A last post-processing that we need to do is manage the fluid reattachment and detachment of particles. So you can see here the representation of a free surface with a node that is going a bit far away from this. And well, at some point, the alpha shape criterion will remove the elements that connect this node to the rest of the fluid, meaning that we will obtain a node that is alone connected to anything. And in that particular case, we'll simply give the node the mass of the elements that were connecting it to the domain before, and apply simply the law of Newton with gravity to compute the displacement of this node in the space. And at some point, the node will reconnect to the fluid by falling in the exact same way than it has been detached before. And this is a small video. I hope that you can see it, which show a bit how does it looks like. So this is a damp break test case. We will come back on this one later. And you can see here the elements and the node that are changing all the time in order to keep a correct shape. And well, a very great advantage of this method is that the free surface is natively represented by the method. Of course, this is a very raw mesh in order to show it, but with fine mesh, you can see that the free surface is much more smooth. But this is for the simulation of a fluid. When we want to do, for instance, fluid structure interactions, we would like also a structure, and this is where we perform a coupling with classical finite element, meaning because for the solid part, generally the deformation is not large enough, so we can simply use classical finite element, and we will couple the two physics by what is called partitioned coupling, meaning that the fluid will be solved by a solver that is not the same solver as the solver used for the solid part. And those two solvers will communicate between each other in order to perform this coupling. And this communication is done according to the Neumann-Dirichlet paradigm, where the information that are exchanged between the two solvers are sent under the form of boundary conditions. So Neumann boundary condition that are sent from the fluid to the solid, and Dirichlet boundary conditions that are sent from the solid to the fluid, and in that case, another form, for instance, of interface displacement or fluid load. Well, and this exchange of information is very straightforward when you have your what we call matching mesh. So the interface view from the solid solver is exactly the same as the interface that is viewed from the fluid solver. So the nodes are matching. You can simply take the data, nodal data from one node, and send it to the node from on the other solver in order to perform this exchange of information. But well, in some cases, we would like to use, for instance, a mesh that is more refined for the solid side, or on the contrary, something more refined for the fluid side. And in that case, we need some kind of interpolation. So I won't explain how this is done exactly, but we use what is called Wedel basis function that will convert it to a matrix. So you have an interpolation matrix that I'll call H here. And this interpolation matrix can simply be applied to the vector of nodal loads or the vector of nodal displacement if you want to interpolate those nodal data from one solver to the other solver. And now how the coupling is actually performed. We will start at the first time step by a prediction of the fluid displacement. So the fluid, of the solid displacement. So the solid here is simply the rectangle in plane line here. So this is our prediction that can be zero displacement if we know nothing. Then we'll run one time step of the fluid solver to obtain a load that this fluid apply on the interface, so on the solid. We'll send this load on the solid solver that will compute a deformation. And this deformation is the dashed line that you can see here. And knowing the predicted displacement at the beginning of the time step and the actual displacement that you obtain after this time step, we compute a residual. And using this residual, we can update the predicted displacement of the solid, then restart exactly the same thing, run one time step of the fluid solver, obtain a new load, obtain a new displacement, obtain a new residual, and like that until this residual tends to zero. And well, this is a bit more detail of how do we actually use this residual to update the prediction. The idea is always the same. You simply take your previous prediction and you add the residual times some factor. This factor can be a constant in the Bloch-Gauss-Seidel method, or something a bit more sophisticated like an inverse Jacobian in interface quasi-Newton method. And how all of this is implemented within a code. So here we are what I may call a Python script that contains a function, MPI function, in order to run the fluid solver and the solid solver on different processes. And the communication will be performed using the MPI function for sending data from one process to another. Of course, for the fluid solver, as we are using particle finite element method, we need some remeshing. So this is why I write remeshing here. And those solvers in practice are implemented. So at the University of Liège, those are house-made codes. The first is called Metaphor. This is simply the solid solver that use classical FEM for large deformation of solid. The second solver that you may guess is the fluid solver that is called PFEM 3D, which is not a very original name, but this is doing PFEM. And the last one is simply the Python script that will perform this coupling. But now I will jump to the second part of the presentation. I will show some simulation that we can do using this method, either the PFEM only or the fluid structure coupling with Metaphor. So the first test case is the dam break that you see at the beginning of the presentation, but now with a mesh that is a bit more refined. So there is a block of fluid that will flow due to gravity and hit a small structure here that will bend due to the weight of the fluid. And we'll study the displacement of the A node here, so the top of the structure with respect to time. So you can see here, well, this is a 2D simulation. Okay. And well, here, so as I said, I plot the data that we obtain. So the vertical displacement of this node according to time. I compare also with the result from the literature in order to show that, well, the result is correct. But what is very important to see in this graph is the top one. So the top graph displays the total mass of the fluid with respect to time. In theory, this should be 100% all the time because there is no evaporation, there is no loss of fluid in that case. But the problem with the particle finite element method, and especially in the remeshing procedure, is that you will remove nodes, we will remove elements, we will add some elements, we will distort some elements, and all of this may change the volume of your mesh. And so as we are simulating an incompressible fluid, the mass will change in the exact same way, meaning that at every remesh, you may add or lose a bit of mass in your system. And at the end of a long simulation, this change of mass can be very high. And so the game here is to use the correct remeshing parameters that will allow to keep the mass as constant as possible. You may see that in this example, I managed to do it more or less, but especially in 3D, this may be very difficult. And if I can give the biggest disadvantage of this method is this part, that the remeshing may generate errors in terms of mass or other kind of errors that we may see later. Well, and you can see that this test case is not very long, so this is only 3 minutes, and most of the computation time is taken by actually solving not the remeshing, not the solid solver, not the communication, but really solving the fluid part of the equation. Well, this is a bit the same idea. So this is a kind of balloon that is filled by fluid that falls from the top of the structure inside this balloon. So I have nothing more to say for this test case. This is just to show it. Well, with once again, the total mass and the comparison with literature. What is a bit more interesting, the third test case, which is a 3D test case. And so same idea, we have a block of fluid, but this time the block of fluid is very close to a kind of hyperelastic gate that will open as the fluid will flow due to gravity once again. So you can see here the example in 3D. And well, what happens at the end of you have some kind of bounding box, and when the fluid particle will go out of this box, we simply remove them. So there is no actual boundary condition at the outlet here. We simply remove the node as they come. Well, in that case, we have also data from literature, but also experimental data thanks to Mr. Antosi, which is still very interesting when we compare results. And that you can see that in 3D, while the computation time is much, much higher, this is still something that we need to improve. And well, those two small test cases are only done with PFEM, so there is no fixed structure coupling. This is only to show that we can do something else that's simply a fluid that flows. So this is an example of heat transfer. So there is a fluid that is heat at different temperature at the left and on its right. And well, you can see the movement and the diffusion of the temperature within this fluid. We can also add surface tension if needed. So this is a kind of big droplet that has initially the size of the shape of a square, and as there is no gravity but only surface tension, it comes back to a sphere as expected. This test case is a bit more complex, so this is performed only by the particle finite element solver, so there is still no free structure coupling with metaphor. However, we are still simulating a melting process, meaning that there is a solid, which is the initial condition, and this solid, in the context of our PFEM solver only, is simulated using two different methods. So the first is to simply set the viscosity of your fluid very, very high to sometimes imitate the solid, or to add what we call a momentum sink, where we add a force on each node, depending on the velocity, to prevent them from moving. The problem with this method is that if a node is solidificating in the air, while the node will simply stay like that, flying, which is not only physical. Whoops, sorry. And so on this block of fake solid, we'll simulate a laser. So this is a laser melting simulation, and the laser is simulated by a Gaussian heat flux that is applied on the top. There is also surface tension evaporation process, and you can see here the block is the purple block here. The laser is applied here at the top. You can see that the temperature, of course, increases. The solid is becoming a fluid, and while moving at the top here. And when we stop the laser, this fluid will restart solidificating, and so the bubbles here that are spherical due to surface tension will stop moving and become solid again. And well, there is two test cases that are a bit more fancy and in 2D. Those are only to show a very important feature from this kind of coupling, is that I can actually use any kind of material law for the solid without affecting in any way the coupling, so the coupling algorithm or the fluid solver. So I can use a solid with plasticity, with isotopy hardening, with frictional contact between this solid and the boundaries of the domain, and all of this without changing anything for my PFEM solver or for my Python script for the coupling. And so this is a test case that is a bit funny to see. So you have a fluid that enter in a box from the left, and due to the pressure that is quite high, it will deform the kind of wall that blocks the outlet and eject it out of the box. Well, this is exactly the same idea. Here I simulate a kind of valve with a security system that prevents the fluid from flowing from the left to the right. But here, as I'm forcing the fluid by boundary condition to flow in that direction, you can see that the security system will fail at some point. In that case, I'm using a different solver for the fluid. This is still the PFEM solver, but with an explicit solver for weakly compressible fluid. And you can see, well, the security system that blocked the outlet, and then it fails because the fluid flow in that direction. And so this is all for my presentation. I hope you enjoyed this presentation, and I am, of course, open for any question that you may have.
Okay, thank you, Martin. Very interesting. So I can just remind everybody that they can type their questions in the question and answer box that you can find on the bottom of the screen. So while we wait for some questions to come in, I have, yeah, so one question, so your remeshing is driven by this this alpha shape criterion. I mean, I say remeshing is so
Yes,
and for example, yeah, this example here, so I mean, I know this is just a schematic, but it represents separation of two parts of fluid. So, and that's driven by this alpha shape criterion. So in the remeshing, do you use any physical information, field, pressure fields, velocity fields, to decide on how the remeshing should be performed, or is it purely this geometric criterion?
So this is a very good question. So actually, right now, we are using something that is purely geometrical. And this is one of the problems, because of course, as this is purely geometrical, we may actually obtain some kind of detachment that in the reality would not happen. And on the contrary, we can prevent some phenomenon to appear due to this criterion that does not take into account the physics. And so taking into account the physics is a work that should be done and that will be done in the future.
Okay, thank you. So two questions have come in. Yeah, but both related to the same topic. So from Renato Wacondio and Aaron English. So can you comment about the mass conservation in the particle finite element method? And so the mass conservation of 5% is quite high. So is there a way to reduce this?
There is actually a lot of way to change this. If you do nothing, if you just use the alpha shape criterion, the loss of the gain of mass that you may obtain is more than the double of the actual mass that you had at the beginning. So 5% in terms of what we had at the beginning is small, but physically, of course, this is still high. Ideally, we would want very 0%. What we can do is, well, first taking into account the physics. For instance, if you create fluid at some point, you may prevent fluid from being removed at some other place of the fluid so that you can artificially keep the mass constant. Or you may think about when you have detachment or reattachment of fluid, you may, when a part of the fluid is leaving the system, but when a part of the fluid is detaching, you may want to reattach it only when the fluid that you lost due to the detachment is the same as the fluid that you will gain when your particle will reattach to it. So basically, based on the size of the element that were connected before and that will connected after. So there is plenty of small ideas to do that. And there is people here in the lab that are really working on that topic, especially.
Okay, thank you. Stephen, you had a comment to make there?
No, nothing from me. Sorry.
Something just to add, something that can be useful to reduce this this mass change is to refine. For instance, you can actually use a mesh that is not where the characteristic size of the elements depend on the location. For instance, if you are closer to the free surface, you may use elements that are much smaller than the elements that are created at the middle of the fluid. And if your free surface is much more refined, of course, all the problem of detachment and reattachment are smaller. They are not zero, of course. You will still gain a loss mass, but in a smaller scale.
Okay, so just to stick to this topic, this mass loss, is that then mainly due to detachment of fluid, or does it include that, or not? And are there any other effects, like just removing some mass due to the remeshing, where you change the kind of the enclosed surface?
So the attachment reattachment is part of the mass change, but it's not, of course, the only phenomenon that changes the mass. And there is, for instance, at the free surface, ideally I would have to draw something now, but imagine that at the free surface, if two particles becomes very far from each other, the element that were forming a part of the free surface will disappear, and you will have some kind of hole at the free surface. And if we, due to those kind of process, for instance, you may also lose or gain mass if you have a fluid that fall that is moving close to the free surface. It will create additional elements during all its path and create mass. Something that can also change the mass of your system is simply the equation. So what we are doing is, from one time step to the next one, we'll move the nodes of our elements according to the, for instance, to the velocity field that you compute from your finite element solver. And by moving those nodes, of course, we are doing an approximation, because we simply take into account the velocity, or ideally the acceleration, but it's never perfect. And that can also change the total mass of your system without taking into account the remeshing itself. So there is multiple factors that change this mass.
Okay, thank you. So another question that's come in from Nassar. How does the remeshing affect the conversions?
So that depends of the conversions that you are talking about. So if I take the convergence in terms of fixed structure interaction, because this is really the topic on which I'm working, so this residual here, if you compute a load of your fluid on your solid, and that you remesh, and you recompute the load without changing anything else, you will also affect a bit this load. So the load that you compute after and before meshing is not exactly the same, because the topology of your mesh may change. So the interpolation that is obtained from your shape function will change too, and you will change a bit this load, and so this displacement, and so the residual will converge slower if you remesh more. And this is why generally what we want to do is to simply remesh only when needed. So ideally, you may compute some kind of distortion factor in your mesh. It can be local or global, to know exactly when you need to remesh or when you can continue like that without changing the topology of your mesh. But now, from one time step to another, within the PFEM solver, there is no remeshing. And so the convergence, this is like classical finite element method. Between two remeshing, there is nothing that changed from the classical FEM, so the convergence is exactly the same.
Okay, right. Thank you. I think that's all we've got time for now. So any further questions we can answer.